So how do scientists approach learning? They do it in a very particular way, often referred to as the scientific method. It's a process for understanding nature. It's based on observing and experimenting. So the key parts are observation, hypothesis, experiment, and formulation of laws and theories. And we'll talk about all of those. We're going to watch this funny little, well, it's not funny, it's strange.
Been training medical assistants to hit the ground career ready for over 40
So many
years.
ads. Watch this odd little video I found on YouTube. There's no words, so I'm going to narrate. There's this guy reading a book, listening to some music. Looking around, he notices the one plant is a lot taller than the other plant. So this is an observation. And then scientists are curious. They're like, well, why is that? Why is the one bigger than the other? What's going on? So he's measuring them to get data, writing that down. And then he's going to think about, well, why might these be different? Why is the one bigger than the other? So you come up with some ideas and then how to test them. His first idea is, well, maybe it's because I'm reading to the one and not the other, or playing music, or maybe it's the sunlight. So they do experiments to find out whether these are affecting the growth of the plant. Computers actually used to look like that. So he's going to read to the one plant and not to the other. This is kind of sounding like an elementary school science project, isn't it? So every day, read to the one plant, not to the other, measure the plants. Repeat, repeat, repeat. Test number 2, effective music. So playing guitar and whistling to the one plant, no music for the other plant. Again, measure the plants every day. You get the idea. Okay, third hypothesis, the sunlight. An experiment to see if this is having an effect. So here's the one plant with an open window, and here's another plant where there's a blind covering the window. And measure the height of the plants each day and see what happens. Something's happening this time. So the results. So reading, nope, that didn't do it. Music, nope. Sunshine, yeah. The sunshine had an effect on how tall the plant grew. Close that so it doesn't start playing ads later. So observation is part of the scientific method. Observation is also known as data. can be qualitative or quantitative. So quantitative data is how tall the plant was. Qualitative data might be, well, this one looks greener than the other one, the quality of it. They're descriptions about the characteristics or behavior of nature. So this is an oil painting of a scientist named Antoine Lavoisier, lived back in the 1700s in France. And he was interested in burning things. Anybody here like to burn things? Secret pyromaniacs? I think that's like a prerequisite to being a chemist, right? I don't like danger, I don't like explosions, but controlled burning of things is so fun, right? So he's looking at burning things, and he was burning things in a closed container, and he noticed that there was no change in mass before and after he burned something. So if you burn a piece of wood in a campfire, it was like really heavy to get into the fire ring, right? You burn it, and what's left at the end, is that heavy? The ashes? No. It's like the mass changed dramatically, right? So that's what happens in an open environment. But in a closed environment, everything's contained, you can burn it, but then the whole container weighs the same after as it did before. And it's like, what's up with this, right? So an observation like this leads to a hypothesis. You come up with an idea of, well, what could possibly explain this? A tentative interpretation or explanation. So he hypothesized that when a substance burns, it combines with something in the air. Okay? So we come up with a lot of what end up being bad hypotheses, right? Science is a lot about failing. You have an idea, nope, that's wrong. You have another idea, nope, that's wrong. You do that enough times, eventually you figure out something that's right. So a good hypothesis needs to be testable. You have to be able to falsify it. A hypothesis involving little invisible aliens that come down and do things in the middle of the night and nobody can observe them, well, that's not testable, right? Because according to your definition, they're not observable. So, that's kind of useless. It needs to be something you can test. And then we test that using an experiment. Experiments need to be controlled. So in our little video with the plants, there was one plant that he was doing things to, and the other plant he was not doing things to. So that's like the control plant, and we're looking at this one to see if it grows differently than the other one. We need to control the different variables. Then the experiment may show that the hypothesis may be correct, it may support that, or it may prove it wrong. And then you have a choice. You can either discard the hypothesis. Sometimes it's like, looking back now, that was just a dumb idea. Just throw that out. Or sometimes we're like, well, that there's something good in there. I just need to modify it a little bit. So you modify the hypothesis, and then you do another experiment to test that. From all of this work, we can end up with laws and theories. So a scientific law is just a short statement that tells what happens. So it summarizes past observations, predicts future ones. Okay? So you've all heard of the law of gravity, right? So here are my keys. Law of gravity, I'm holding them out. What's going to happen if I let go? I'm going to fall. Law of gravity predicts what's going to happen every single time, right? Does it explain why? No. Scientific laws can be experimented upon. Occasionally, we get new information that proves them to be incorrect. But for the most part, so far nobody's been able to disprove the law of gravity, and I don't recommend trying that. Right? So the laws come from those observations. A theory comes from tested hypotheses. So hypotheses that appear to be correct can form the basis for a theory. It's a model for how the way nature is and tries to explain not just what it does, but why. Why does it do that? So gravity is something that's not fully understood even today. So there's no great theory of gravity. We understand some parts of it, but it's still not all understandable. So from Lavoisier's work, did I miss something? Yes, I did. I forgot this part. The law of conservation of mass is what came out of Lavoisier's work. In a chemical reaction, matter is neither created nor destroyed. So when you burn something, you're not destroying it. It looks like that, but that stuff is all still there because you weigh it before and after. The mass is the same. The theory that explains that law was published by John Dalton. He lived a little bit after Lavoisier, the atomic theory. So it explains that law by saying matter is composed of small indestructible particles called atoms, and in a chemical reaction, we're just rearranging those little particles, and that's why the mass doesn't change. So that's the explanation. Theories also are validated by experiments. One thing that's, really somewhat disturbing is we cannot prove anything to be true. We can prove things to be false, but we can't prove that something's true because we may discover something in the future that causes us to realize, well, that actually wasn't true. So the best we can do is a whole bunch of people have tried this and nobody can find a problem with it, so we think it's true. That's the best we can do. So a well-established theory is as close to truth as we can get in science. It would be nice if the scientific method was just a list of steps, do this, 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 and this, and you get this outcome. But it's not like that. It's very messy. So you could look at it this way. Here's some observations which might lead to a hypothesis, and then you test the hypothesis, and maybe that experiment confirms your hypothesis, right? Well, then somebody else is probably going to test it. You'll do different tests. It's like, okay, well, we can't find anything wrong with that one, so maybe it becomes a theory, which is still subject to being tested. If your first hypothesis is wrong, then you may need to revise the hypothesis and test again. Those experiments can also lead to a law. It's a summary of observations of what happens. But you can spend your whole scientific career going around in a couple of these circles. Scientists actually end up spending most of the time proving themselves wrong. So we're just comfortable with failure. Because failure is not necessarily a bad thing, right? You've learned something. I now know that this doesn't work, right? So I'm going to try the other thing, and another thing, and another thing. And eventually, maybe you find something that does work. So here's a question. Which statement best explains the difference between a law and a theory? A law is truth, a theory is mere speculation. B, a law summarizes a series of related observations. A theory gives the underlying reasons for them. Or C, a theory describes what nature does, and a law describes why nature does it. B. Yeah, it's B. C is real tempting because I kind of said something very much like that, but what I said was a law describes what nature does, and a theory describes why. So C is exactly backwards.